Bismillahirrahmanirrahim. Assalamu alaikum. Welcome back to your online lecture series of EE222 microprocessor systems. This is your second lecture of week 10, lecture number 29, and in this lecture we are going to discuss the watchdog timer, its uses, the input-output port structure of PIC microcontroller, pull-up resistors, implementing the digital clock using assembly language, and data serialization using the rotate command in PIC microcontrollers. This will be the last lecture of your assembly language programming, your CLO3, and from next week, inshallah, we will start your CLO4, that is programming the PIC microcontroller in embedded C language. Okay, so let's start our lecture with the discussion on watchdog timer. In our previous lectures, the students faced a problem that after a certain time, their program was automatically resetting after a certain time. And once we cleared or turned off the reset enable of the watchdog timer, the issue was solved. So what exactly is a watchdog timer? What is its purpose? And when to turn it on and when to turn it off. For now, let me tell you in advance that in our basic applications, we are not going to use the watchdog timer, but later on, if you are developing some sensitive equipment that needs to be checked after a certain time, and you have to be very sure that your program is working fine, you will need a watchdog timer. What is a watchdog timer? It is simply a timer that is running continuously in the backend. So when we turn on the watchdog timer, the second option we get in the configuration bits is the overflow time. For example, if I set the WDT time to 300 milliseconds, the watchdog timer will start running, and after completing 300 milliseconds, it will overflow and it will start running again. But once these 300 milliseconds are completed and the watchdog timer overflows, it will automatically reset your microcontroller. So it will count from 0 to 300, and once it overflows from 300 to 0, it will reset the device. So what is the purpose of this timer? If due to some error or disturbance or noise, your program gets stuck in an infinite loop and does not come out of it at the desired point, the watchdog timer is already running in the backend, and it will reset the microcontroller once it overflows. Otherwise, if your program is behaving normally, you have to manually reset this watchdog timer after certain intervals. For example, if we have set the overflow time of watchdog timer to 300 millisecond, we have to reset it after every 299 seconds at least, 299 milliseconds at least, to stop it from overflowing and stop it from resetting the device. So for example, this is your loop 1, this is your loop 2, and this is your loop 3. This loop takes around 200 milliseconds to run. This loop takes around 170 milliseconds to run, and this loop takes around 300 milliseconds to run, or let's say 360 milliseconds to run. You will see that now this 360 is greater than 300. So what you want to do is you want to change your reset time or overflow time of your watchdog timer to at least 400 milliseconds. What you will do is you will run this loop. It is supposed to complete in 200 milliseconds, and if it is completed in 200 milliseconds, it will come out of the loop and come here. So at here you will manually reset the watchdog timer. Then the program will enter the second loop, and if it runs as expected, it will take just around 170 milliseconds to run this loop. It will be finished and the program will come out of the loop to this point, and at this point you will again manually reset the watchdog timer, and again same goes for this loop. But what if there is some mistake in your program, or there is some this loop is dependent upon an input. For example, this is a delay loop, and this delay loop is dependent upon an input that we are taking from a port. For example, if this is a delay loop and this delay loop is in milliseconds, so whatever milliseconds into input, so this input is coming from port A. Now we assume that port A's value can be between 0 to less than 36, you can say, and here you can say it is 10 milliseconds. So if port A's value is 36, it will be 10 into 36, 360 milliseconds. But what if due to some error or due to some noise, this value becomes 44? Then the delay will be 44 into 10, 440. So this loop will be stuck, the program will be stuck in this loop for more than 360 milliseconds as desired. But we have a fail-safe watchdog timer running at the back end. So that is supposed to reset the microcontroller if your program is stuck in any loop for more than 400 milliseconds. So in this case, if there was an error or there was a garbage value at port A that caused this loop to run for more than the desired time of 360 milliseconds or 400 milliseconds, the watchdog timer will overflow within this loop while it is in this loop, because we have not come out of the loop to manually reset the watchdog timer. So within this loop, this watchdog timer at the back end will overflow and it will cause the controller to reset, and it will start from ORG00 again. So simply watchdog timer is a fail-safe timer, and that is manually reset by the computer after certain intervals of time to avoid elapsing this timer. And if due to some reason, due to some error, the user or the computer is unable to reset this watchdog timer manually, it will overflow and it will cause the computer to reset to come out of that infinite loop of the error. So here in PIC18, in a 40-pin package, PIC18F4550, PIC18F4550, that is a 40-pin package, we have port A, that is a 7-bit port, and its pins range from 0 to 6. Then we have port B, that is an 8-bit port, and the bits range from 0 to 7. Port C is again a 7-bit port. Its bits range from 0 to 2, 3 is missing, and then 4, 5, 6, 7. So pin 3 is RC3 is missing. Then we have port D, that is again an 8-bit input output port 0 to 7, and then we have port E, that is a 4-bit port from 0 to 3. Why am I telling this again and at this point? Because today we are going to make a clock, and to make a clock what we need is we need 3 8-bit ports. We have to connect two BCD displays for seconds on one port for PIC BCD numbers. Then we have to connect two BCD 7-segment displays on one 8-bit port for minutes, and then same for the hours. So we need 3 8-bit ports, but we only have 2 8-bit ports. So for instance, we can use the port B for seconds, we can use the port D for minutes. What about the seconds? We can use port A because it is a 7-bit port for the hours. How can we use port A for hours even if it is a 7-bit port? Wouldn't it cause any issues? Let's see. This is your 7-segment display, BCD to 7-segment with a built-in BCD to 7-segment decoder, 1 2 3 4. So let's assume this is port A 0 1 2 3. So this can count from 0 to 9. Then if we connect this one to port number 4 and 5, and we connect the uppermost significant bits to ground, it can count from 0 0 0 1 1 0 1 1 from 0 to 3. So in total these two displays can count from 0 0 to 39. But even in the 24-hour system we count from 0 0 to 2 3, and for a 24-hour clock, and for a 12-hour clock we count from 0 0 to 1 1. So it serves our purpose. Even if we don't have the upper 2 bits available, if the bit RS6 is being utilized for HS oscillator, so we don't have the uppermost significant 2 bits, but it serves the purpose, and we can use the port A as our hours port. So we will use this configuration to design a complete digital clock in today's lecture, and I'll guide you step by step how to make the loops. Okay, so let's start making a program for a digital clock, that a 24-hour digital clock that will display the hours, minutes and seconds on the binary coded decimal 7-segment displays. First, let me equate the count for seconds, minutes and hours. C means equate 0 cross 0 0, and CHRS equate 0 cross 0 0. I will always recommend you to give names or labels to different locations, and that will make it very easy for you to develop your program logic and to decipher and debug your program later. So once I have equated the 3 file registers that will hold the count for seconds, minutes and hours, let me give the names to the ports also. Seconds equate port B, so I will be using port B to display seconds. Minutes equate port D, and hours equate port A. As discussed earlier, we will use port A to display the hours. Then for the delay, again I will use R1, R2 and R3. So R1 equates 0 cross 0 3, R2 equates 0 cross 0 4, and R3 equates 0 cross 0 5. I think we will not need any other variables, but we'll see. Let's start writing the program, and if we need any more variables, we will declare them. So let's originate our program from location 0 heads up. Clear F, press B, clear F, press D, and clear F, press A. I have made all the ports as the output ports. Port A, B and D, that are for hours, minutes and seconds. Okay, so as we know that our port A is the pin 0 to 3 of port A is by default set as analog input. To make it as digital input output, we have to move 0 cross 0f literal value to addcon 1. Up till here our basic settings are finished. So let's start by making a loop, and let's start with the seconds loop first, and then we will keep building the program around the seconds loop, the minutes loop, and then finally to the hours loop, and we'll close them all together. So in the seconds loop, we know that we have to count from 0 to 60. So let's move a literal value of 60 to the count for seconds. Let's initiate these values for minutes and hours also. So let's move a value of 60 to for the count of minutes also, and then 24 for the count of hours. Now we want to keep incrementing our seconds port, call a delay, and then check whether the count for seconds exceeded 60 or not. So we will move a literal value of 1 to the working register, then we will add the working register and file register. Which file register? Seconds, our port. So the port designated for seconds will be incremented. We will decimal adjust, and the result will be stored in W register, and then we will decimal adjust the working register. So now the working register contains the incremented value of seconds, and that is BCD adjusted. Now we have to move this value from the working register to the actual port, that is our seconds. Call a delay of 1 second, and then decrement file register and skip it 0. Which file register? Our count for seconds. If the count is not 0, just simply go to, again keep repeating the same loop and keep incrementing the seconds. Where we are incrementing the seconds? At this point. So let's give this point the label of again. What if after decrementing the count it becomes 0? So it has completed the 60 counts. After completing 60 seconds, what we want to do? We want to increment the minutes by 1. So we will move a literal value of 1 to the working register, then we will add the working register to the file register. Which file register? The minutes, and store the result in working register. Why we are storing all the results after addition in the working register? Because we want to decimal adjust the result, and the decimal adjust command only works on the working register and not on any other file register. So the result is now in the incremented result is now in the working register. Just decimal adjust it and then move it back to the minutes port. Again decrement file register and skip if 0 the count for minutes. Now when the count for minutes is not 0, what we want to do? Let's say it was the first time it came to the minutes loop, so it was then the minutes will be incremented from 0 to 1. What we want to do next? Start the seconds again from 0. So let's go to reset seconds. Where should be reset seconds? Here is our secs, reset seconds. But we can see that it is resetting the minutes and hours also. So what we should do is we should move them above the seconds. The hours should be the outermost loop, then the minutes, and then the seconds. So now I think this is in the right order. So it will reset the seconds and it should also clear the port of seconds. It should also display 0. It is resetting the count and it should also reset the display to 0 and then call delay. After calling the delay, resetting it to 0, and then it should remain 0 for 1 second, and then again it will start incrementing the seconds routine. Then again coming to the minutes routine and checking whether the minutes counter was overflowed or not. So now let's assume the minutes counter was also overflowed. So what it should do? It should increment the hours. Let me copy and paste this subroutine. It should increment the hours, decimal adjust it and send it back to the hours. Then it should decrement the count for hours. If the count is not if the count is not overflow yet, what we want to do is we want to reset the minutes. Otherwise we want to reset the hours. If the hours count is also finished, we want to reset the hours also from 23 to 0. So RHRS. To reset the minutes, we want to give the label here R means, and then to reset the hours we have to give the label at this point. Now all what's left is the delay subroutine. So again I will copy the delay subroutine of my previous code that was written for 1 second. Let's compile this code to check for any errors. Oh, there are many different errors. Let's start with the first one. Just click it. SECS equate port B. Oh, okay. We have not included the library hash include P18 4550.inc. So let's include the configuration bits by going into the window, then target memory views, and then the configuration bits. So here are the configuration bits. What we want to do is we want to use HS as an oscillator, then power reset is off, brownout reset is off, watchdog timer is off, port AB enable is off because we want to use them as digital IOs, and stack overflow underflow reset is off. generate the source code, Control A, Control C, and paste it on top of your code. Let's build again. Many warnings but no errors, so our code has been compiled successfully. Now here is the Proteus file that I have made for the simulation of this particular code. So in this file you can see that we have already selected the lecture 26 production.hex, and this is our lecture 26. We have used two displays, 7-segment displays connected to port B for seconds, then port D for minutes, and then port A for hours. And we can see here that I have connected the uppermost bits of the tens counter of hours to ground. Let's simulate it. Okay, so the results are not correct. Now let's see what is the problem with this code. Okay, let me clear CLRF, SECS, CLRF, MINS, and CLRF HRS. Let me clear the initial value of all the ports. Let's build it again and let's run it again. Okay, now so it is working fine. It is working a bit quickly, but it is working pretty good. After 59 seconds, the seconds counter should overflow and the minutes counter should increment here. If I further reduce the delay, you will be able to see that even our hours counter is working fine. I have run the code for few hours and the code worked without any issue, without any reset. So this is your code for the digital clock. I am not going to provide the source file of this code to you guys. I think you should type it and write it yourself, because in this way you will learn more. If you just copy paste and run my code, definitely I have already simulated it, so it will work. But once you write it yourself, there you may have some typing mistakes, and you will get to rectify the errors that you get in your program. And secondly, once you are typing it yourself, you will get to understand the logic in a better way. Okay, so let's come to the last topic of today's lecture, that is data serialization. What is data serialization? Let me first ask, what if you want to send a data from one microcontroller to another microcontroller? This is your sender and this is your receiver. So if you want to send data from this device to this device, what you can do? Let's say it is an 8-bit data. So the simplest thing that comes to our mind is to connect the two 8-bit ports of the sender and receiver together through an 8-bit line and send the 8-bit data directly from the sender to the receiver, put it on the output port of the sender and make the port of the receiver as an input port and read it. So the 8-bit data will be transferred in parallel from sender to receiver. But let's say these two devices are far apart. Then it is not feasible to connect these two devices using 8 separate lines. And let's say this is not an 8-bit data, let's say this is a 16-bit data. So if these two devices are even 100 meters apart, you have to use 1600 meters of wires as connections between the sender and receiver, and also some ground and VCC. So that will be too much. That will not be a feasible solution. The only advantage of parallel data sending and receiving is the speed. All the data bits are transferred at a time. But what if it is not physically feasible? What other options do we have? Only for sending or receiving a data from one end to another end, we can use a single line. Only one bit, single line from the sender to the receiver. We know that all our data is in the form of ones and zeros, and they are present inside a register. So what if we take this single bit one by one and keep sending it to the single bit of the sending of a single pin of a sender, let's say RB0. For example, if we just push it, if we just rotate it, this 0 will pop out and send this 0 on RB0. Then push it again, so the 1 will pop out and push that, send that 1 to RB0. And similarly, keep checking the transitions on the receiver side. It will transfer the data like this. So what is this data? 1 0 0 1 1 0 0 1 1 0 0 1 1 0 0 1. This is 99 hexadecimal. It will be received on a single port through a single pin, but it will be sent one by one, one after the other. How to do that manually? In PIC microcontroller, we have a command, or we have an instruction RRCF, rotate right with carry a file register. Let's say file register data. I have equated data to location number 0x00. So I have some data placed at location 0 and I rotate it through carry. When I rotate it through carry, this digit that pops up goes into the carry. It is not flushed out. It is not wasted. The popped up bit goes into the carry so that it is saved somewhere from where we can read it and we can send it to some other microcontroller or to the receiver. So once we rotate it, this data, the rightmost bit, the least significant bit, will pop out and will go into the carry. So what we can do next, branch if carry where set bit, otherwise BCF port B0. Go to again, and here it is set bit BSF port B0. Go to again. What this program is doing is, I am taking the data from location 0, rotating it once, so the rightmost least significant bit will pop up and go into the carry. Then I am checking if there was carry, go to the label of set bit, otherwise clear the bit of port B and go to again. Rotate it again, so the second bit will pop up, go into the carry, and again go here. Branch if there is carry to set bit. Let's say this time it was 1, so it will come here, set the port B and go to again. This loop will keep running infinite times, but we know that the data in PIC microcontroller is only 8-bit, so we can make a counter of 8 and we can run this loop only 8 times to send the complete data. Now a question arises that what is the value of this time? After how much time the bit will change from 1 to 0? That depends upon the protocol and that determines the speed of data transfer. For instance, if I say that after 1 microsecond my data will change. For instance, there are two ones. The bit is not changing, it is always 1. There was 1 and then again there was 1. So how will I know, how will I distinguish that these are two ones, this is not just a single one? I will check for 1 microsecond at the receiver end and I will see that if the bit changes after 1 microsecond or not. I will push it as a next bit. I will take it as a next bit. After each 1 microsecond at the receiver end, I will manually change my bit number and I will keep receiving this data in the similar manner. To write a code for receiver will be your assignment. You can take help from Mazidi's book. The data serialization is section number 5.4 in your Mazidi's book. It is page number 195 of the PDF file and it is page number 179 of the actual book. Chapter 5, section 5.4, rotate instruction and data serialization. From there you can see the program for sending and program for receiving, and I will give you an assignment based on these two. So at this point, the assembly language programming of our PIC microcontrollers are finished. From the next lecture, inshallah, we will start using the embedded C language for programming the PIC microcontrollers. We will be using the same MPLAB X IDE for that purpose. C is a higher level language and first it is compiled and then it is assembled. So there is a two-step process. Assembly is the lower level language, so it is just assembled into the machine language code. So that's it for today's lecture. I hope you have understood the basic operation of PIC microcontroller and the basic instruction set and programming the controller in assembly language. If you have any questions, again, use the week 10 channel on Microsoft Teams. I hope your live interactive session will be tomorrow at 4 p.m. Saturday, that is Saturday, May 9th. So please be ready for that. We will discuss about the PIC architecture and assembly language programming in that session. And from next week, we will move on to the C language programming, inshallah. Till then, take care. Allah Hafiz.